All right, welcome to Lesson 8. We're going to talk about integrating mechanical systems. And as always, I want you to review the learning objectives that are in the training guide so that you can fully understand what it is that we're going to be talking about. But predominantly, we're going to talk about the three trades, which include the electrician, the plumber, and the HVAC contractor. These are the three trades that affect the SIP build the most. You as the builder or the installer need to understand how you're going to communicate with and how you're going to relay the information necessary so that the work they do doesn't affect the work you do adversely. Now, why should you care? Well, for one reason, it's going to make you a more efficient builder. It's going to make the installation go smoother. It's going to keep everybody on the job site happier. And that's good because we don't want negative problems. Far too often I hear the comment about electricians suggesting that SIPs are too hard to wire. And in some cases, I'll even knowingly jack the price up by 10 or 15, maybe 20% or more because they think or they feel that working with SIPs is difficult. The plumbers don't like it because they think, oh, now I've got to push piping through a solid wall. I can't get my pipes where I want them to go. HVAC contractors usually aren't too terribly affected. They just do everything by rules of thumb in some cases and go on their merry way. So we want to talk about these three specific different trades and how you're going to work with each of these three trades to make sure that the job comes out successfully. And identifying these three trades are the ones that I've discussed: electrician, plumber, and HVAC contractor. I've said it before and I'll probably say it again, but it's key that you meet with these people in a pre-construction meeting. A pre-construction meeting should be with these three trades specifically because the one thing that you need to do is explain to them the fundamental change in the building process. As I said before, when we build houses conventionally, the insulator typically comes after these three trades. And if they don't understand that, they don't know that the work you've done installing SIPs is installed, sealed, and hopefully the work they do doesn't mess that up. So in pre-construction meeting and in the design phase, speaking with these individuals, it's very important that they know this house is already sealed. The insulator has already been there. Now when they do their work, we don't want them coming in there and chopping big holes and cutting things into this wall or the roof assembly, the envelope, that we can't repair so that we can maintain that airtight envelope that we're hoping to achieve. So in the pre-construction meeting, it's important to identify things like, let's know where we're going to have every penetration in the entire envelope. Identify them on the plans, know where they're going to be, and know what size they need to be. We want the proper size penetration so that as whatever goes through that hole, there's still enough room to properly seal around it. And that's very important. Let's start out with the electrician. He'll be the first one that we talk about. And I got to say, is it really that hard? I don't think so. I've wired enough SIP panels to know that with a little planning, a little forethought, it can be done just as quickly as in conventional framing. In fact, I've worked with enough electricians and trained them and shown them the way to run electrical in SIPs that by the end of the job, it's not uncommon for them to say, I would just as soon wire a SIP house as I would a conventionally framed house. I can do it just as quick. Because there's no studs to drill, because there's no staples to put in some cases, they may even be able to do it faster. And I'd like to suggest that you as the builder or the installer have the potential to ensure that it goes faster, to ensure that it's more profitable for the electrician, which makes him happier, and he's more inclined to come back and give you a good cut rate prices and do the job that you're doing. But in order for all that to work, there's one key element that has to happen. You, the builder installer, has to be part of the pre-planning process, and you have to be part of the communication process. And what do I mean when I say communication? I mean communication as simple as that black marker that you keep in your pouch and you identify where chases are and what you've done for that electrician so that when he shows up, he knows where chases are in the wall. He knows how he's going to get wires from point A to B. And it's that type of communication that allows the electrician to successfully move through the installation of his wiring without fumbling around and drilling holes and hacking access into the wall panels as he shouldn't, because you want to know exactly how he's going to go through it and you're working with him to know how that's going to happen. Now, as part of the pre-planning operation, it's not just the electrician that should be part of that. When we're talking about the design phase, it's also important that people like the architect, the homeowner, as well as the electrician are part of that pre-planning, because this is the time where we determine where a lot of things are going on. Where are the lights located? The fixtures, specifically ceiling fixtures and ceiling fans. These are the type of things that help us in the design phase then plan for where electrical chases are going to go. So the pre-planning isn't just you and the electrician on site. It's pre-planning all the way back to when you're sitting down, and even as far back as you're thinking about estimating and quoting the project to know how much electrical work there may be and how much assistance that might be required. When it comes to electrical chases in panels, there's some standard layouts. Most manufacturers include electrical chases, whether they be horizontal or vertical, in a standard configuration. For instance, they might have a horizontal chase at 14 inches for plug height, perhaps 42 inches for a switch height. They may go a little bit higher in the kitchen when you have plugs around the kitchen countertop. And then every so often they may put vertical chases. Now, as a standard, some manufacturers might suggest, well, here's the panel and it's got all these chases in it and you've got them to use where you need them. But this may be a case of having something and not needing it, or do we need it and we don't have it? I'd rather need it and not have it, knowing that there are methodologies that we can use to put chases where we need them in the field. And the reason I say that is because I'm always considering the air infiltration and how air is moving through this system. We want this envelope as tight as we possibly can. And if we put a highway of conduit chases through our foam core with the ability for air to get into those conduit chases, then air is going to move freely through the entire envelope of our system. That doesn't necessarily make a good deal of sense. So I encourage you, the builder or the installer, to think about, where do I really need these chases? For instance, where do most switches go in all of builds? They go right next to the doorway. Well, there's a very simple way to put chases behind doorway bucks so that we don't need this 42-inch high horizontal chase around the entire structure. It's a chase that we may never need and don't necessarily want to have to go back in and fill it up. So let's not necessarily put them in there just because we think we may need them. Let's spend a little bit more time planning about where we know we're going to need them, and then make sure that they're inserted by the manufacturer in the factory, and then when it comes time to install them, we've got the chases we need. Now, this standard electrical chase that the manufacturer provides is typically going to be 1.5 inches in diameter, and as described just now, they go through that standard configuration of horizontal and vertical runs. Pay attention about how we're going to incorporate these electrical chases. When you get on site with a SIP, the tools that you have, or that the electrician who's experienced with SIPs has, allows him to drill through, core into the foam to give him a chase wherever he needs. Or more importantly, you, the installer, as you set panels, have the ability to use simple 1.5-inch auger bits to core into or drill into the core of the panel and give that electrician access when it's only short distances. Going up towards of 2 or 3 feet for access for the electrician is not uncommon and not difficult at all. And once you make that core drill, you're going to mark it, you're going to label it. You're going to give that electrician access from floor to floor or from basement up to first floor so that he is able to pull those wires quickly and efficiently, because it's very difficult to drill that hole after you've assembled all the panels together. So there's certain tools that we're going to assemble to make sure you as the installer are going to use while thinking about that electrician. You may even go so far as to cut box openings. It's not difficult to assemble a quick jig with a plunge router and incorporate box openings such that the electrician, when he shows up, it's as simple as pushing wires through the chase, setting his box, and he's never had to pull another tool out of his tool belt, like staples and hammers and drills. He's ready to go. Pretty simple to do. Now, if you need to put a chase into an EPS core panel, the expanded polystyrene, if you remember back at the beginning, we talked about how it has a melting point. This is another case where we can use that melting point to our advantage. We use what's sometimes referred to as the hot ball technique. By taking nothing more than a 1-inch chrome steel ball heated with a propane or MAP gas, we can literally put a vertical chase, and I say vertical because gravity tends to work in that direction. Depending upon how you orient that panel, you may make it a horizontal chase, but we can literally go into this panel and we can melt on site a wire chase through the core of the panel. It doesn't work for a urethane panel because, again, the urethane will just char. You'd have to core drill it. Other tools that we might want to use to get these chases through panels are going to include flex bits. The number one tool that I typically use is a hole saw, and that hole saw gives us access into the panel. It gives us a way to get our fingers in there, get to those internal chases and grab wires. The other key thing about putting wires in panels is it's a lot easier to push them than it is to pull them. Nothing more than bending over the end of the wire and taping it so we've got a blunt edge allows us to push wire through wire chases and it doesn't dig into the foam. It's actually much easier than pulling the wire. Just one of those other little things that we make it easier for the electrician. When it comes to exterior outlets, this is where we really want to start paying attention. The electrician should have already told you where the outlets are going to be, or maybe the homeowner or the architect told you where exterior outlets are going to be. But these outlets need to be put in, and we need to know exactly where we're going to go back in and foam them up to seal them up tight. It's important. Now, I already mentioned about switch legs and door openings. This illustration will show you how we can bore through the lower sill plate with an 1.5 inch or 1.5 inch bit. This allows the electrician to have somebody below pushing the wire up through, and then we can bury that wire into the foam core behind the door buck as illustrated. Makes it very simple. Picture on the left here is showing us how, as we install panels, the electrician may have identified on the print where a ceiling fan or a chandelier is going to hang out of the ridge of a roof beam. Well, you can see the wire is already hanging out of this ridge, and it's hanging there because the panel installer took the few simple steps he needed to make it easy for the electrician. Now, I'm not just trying to sugarcoat everything for the electrician, but let's face it, you want things to go quickly and smoothly, and you don't want to be overcharged. And having the electrician cut a home run circuit wire and having you lay it down into the ridge of the panels before you seal it up means a lot of good things have just happened. You've made the electrician happy. You didn't spend a whole lot of time putting a home run circuit where it needed to be, and you were able to seal up and finish your ridge, finish the work up on the roof with the wire already in place, and walk away knowing that your roof assembly was sealed up tight. The electrician doesn't have to come back up and get in there and tear into it. Now, the picture on the right shows a different scenario. In this case, the electrician may have shown up before you got there with the panels. This adds a little element of twist because once those wires are in place, you, the installer, may have to work around them. You can see in this photograph that we can identify cover plates or steel protective plates because the electrician has grooved timbers below that T and G and buried the wire, and now that he's covered it back up per code with something that prevents it from being cut or penetrated when you attach the panels. This also may be done with electrical conduit. You may have conduit buried in somewhere so that now once the panel goes in, you've got to watch out with the when you attach so that the panel screws don't go through those conduit. Trust me, I know from experience, you can run a panel screw through a piece of conduit. And if you do that and you're not aware of it, you may have a roof on, a roof finished with shingles and everything before the electrician shows back up to pull a wire through a conduit that he can't get a wire through. Now you got a real problem. So it's important to remember, if the electrician's already been there and done some of his work, and you start installing panels, you have to stay out of his wiring, you have to stay out of his conduit, be aware of where he has run everything. It could get you in big trouble. I'm going to show you this illustration, and this is a perfect example of how an installer, after the panels were installed, we've got wires dangling from the ceiling. The electrician may have cut and labeled the circuit, has provided it to the installer, but the installer took a couple of extra steps to drop that wire down through the hole. He's already up on the roof anyway. It's not that difficult. If we've identified where those chases are, it's pretty simple to run that wire down, drill through, and drop it in place. Labeling chases. By far, when it comes to working with your electrician, it is the most important thing to do. If you're lucky, the manufacturer that you're using may pre-wire the panels such that there's a label that shows exactly where that wire chase already is. If it's not there, mark it. Know exactly where that wire chase is. The picture on the right shows how we've labeled not only the deck, but the panel as well. The hole on the label on the deck shows where we've bored through the sill plate and given the electrician access into the wall, and the mark on the panel verifies that the vertical chase that's in the panel is in a line with that mark below. As I mentioned before, in some cases, the electrician may have a little bit of difficulty getting in some places, and if you've identified these in the pre-construction meeting, it makes it a lot easier. One of these areas that goes along with a detail that we like to use is the hanging floor system. So I'm often asked, well, how am I going to get from first floor to second floor wall panels if I've got a hanging floor system? Well, this scenario of slides is going to show you very simply how we do that, and I'll just walk you through it. We've got what shows here to be a hanging floor system going on the lower floor. Once that upper sheathing is on and we're on our second deck, now we're going to put down our sill plate, and before we stand our wall panel up, we're going to do exactly what we did in the first floor wall panels. We're going to identify where we want that electrical to be able to come up into the second floor wall panel. So we mark, identify, and then drill with our 1.5-inch auger bit down into the top of the first floor panel and up into the bottom of the second floor panel. And those two vertical chases are in perfect alignment. They're aligned and they're labeled. Once that panel goes up on the second floor, the only thing that separates it is the sheathing and the sill plate, and they're drilled as well. So once we pull these together, now the electrician can pull out one of his favorite tools, which is the hole saw. 3.5-inch, maybe a 4-inch hole saw allows the electrician or yourself to make the access through the skin of the panel so that you can now find these chases, and we can very simply snake our wire along through the floor system in the lower hole saw cut, come up through those sight chases that we cut, and then maybe horizontally along a factory cut chase, or if we had to cut that chase ourselves, we can do that as well with the panel. Again, we're thinking about how wiring is going to get to areas that it needs to be. Personally, when it comes to putting wires into vertical chases in panels, I typically go into the design stage and I think, where am I going to need this vertical chase, and only will I ever put a vertical chase in that particular area. And that's where I don't have floor systems to work through, interior partitions to work through, or some other means. And that's the only place that I'm going to do that. Now, if we get into the commercial world, things change a little bit. Once we get into the commercial world, the majority of the times, we find that the electrician doesn't have the luxury of just pulling a Romex wire. It needs to be shielded in some way, or it needs to be in conduit, and that can add a level of complexity. The first thing we typically do is we increase the size of the chase. Instead of a standard 1.5-inch chase, we may bump that up to 2. Why? Because now we're dealing with a metal shielded or a Smurf tube, and that Smurf tube can be pushed through that chaseway if it's a little bit larger, just a little bit easier. Here you can see that up on top of the roof, we've got a metal shielded conduit wire that runs to boxes. We have access up on top of the roof to take that box and screw it down into the panel, foam up around it completely, and the plug that you see lying on the roof is that plug that was removed when the hole saw access was made. We can simply take that plug and we can foam back up around after the electrical rough-in is completed, and we can seal it back up 100%. That's exactly the way we want to do it. Now, if you don't have that pre-planning meeting, if you don't work with your electrician, if you don't have the tools and the techniques and the understanding about how to move wires through walls, this is the kind of thing that can happen, and this is what you don't want to see. This involved an electrician who never got any training, didn't know how to get his wires from point A to B, so he simply grabbed his router or his skill saw and started grooving the panels anywhere he needed to run a wire. He literally has destroyed the panel from a structural standpoint because he's now created what would be a hinge joint in this panel. It's lost its ability to handle that lateral load. Now, some people might say, well, I've heard you can groove a panel vertically, but not horizontally. And that's not exactly true, because if you have a wind load, which is a lateral load, it doesn't care if that hinge joint is vertical or horizontal. That doesn't mean that there aren't methods to take small sections of grooving and still not destroy the structural integrity of the panel and tuck that wire in there. But certainly nothing like what you see here would you ever want to see when you walked into your job site after leaving your electrician alone for a day. Now that we've gotten the electrician out of the way, the next tradesman we want to speak to and make sure that he knows what he's doing when he's working with our project is going to be the plumber. Now, the one thing I like about working with plumbers is when they look at a SIP package, they instantly don't want to be in the exterior walls because they think it's difficult because they've got a foam core in their way. Well, that's a good thing in my book because that means we can get all of our plumbing out of our exterior walls. In some areas of the country, that's actually almost mandated because of the climate, because of the fact that we don't want to violate or destroy the integrity of the insulation. If I had my ways, there would never be any plumbing in exterior walls whatsoever. But if we do need to put plumbing in exterior walls, we need to design for it. We need to plan for it. Well, how are we going to do that? The nice thing about working with SIPs is we can mix and match systems from SIP system to conventionally framed system. We can go from a thick SIP to a thinner SIP panel in a certain area, and we can create chaseways. We can create a path for that plumbing to move through it. If we need a vent stack and it has to go in the exterior wall because there's just no other place to put it, we can accommodate it. It just means that you should plan for it. Again, just like you didn't want the electrician to show up cutting through your panels unknowingly and ruining the structural integrity of your panel, the plumbers have been known to do that too. It's all about the planning process, so make sure you work with them to know where they need to be in the exterior wall. Now, my preference would be, of course, to go to that interior partition. So start thinking about that all the way back in the design phase when you start thinking about the layout and where is an interior partition that we might be able to use for things like vent stacks and drain lines. Studer vents or air admission valves, one of my favorite things that was ever invented for plumbers, because it means that we don't need to put a vent immediately right where that kitchen sink is. It means we can put a Studer vent and tie into a main vent further down the line, perhaps where we're in an interior partition. We can combine vents. We want the fewest number of penetrations through our entire SIP envelope as we possibly can. And combining vent stacks, combining things like drains and everything that's going to move through our wall makes a lot of sense. That's part of your pre-planning meeting, to sit down with these guys and say, let's see if we can get the number of penetrations through my SIP envelope down to the bare minimum. How are we going to do it? We can look at plumbing chases, which means we're no more than like building a wet wall, perhaps. If we have to get plumbing on the exterior wall and we don't want to violate or interrupt the integrity of our SIP envelope, we can simply build a framed chase. And that framed chase allows us to take plumbing and any other mechanicals for that matter from floor to floor or up or down in either direction. It's just a framed chase. If we don't allow for and plan for that framed chase or that electrician, these are the kind of things that we start to see. This plumber was left to his own vices and he just started hacking into the panel. This section of plumbing is now in a place where it's destroyed the structural integrity of the panel, not to mention he dug out a huge amount of the foam, did make the obvious attempt to foam in back around it, but I don't think they're going to get quite the insulating values that they would hope to have. Remember we talked about penetrations and how we want to cut the right size hole. This is an example with this plumbing water line going out through the exterior wall, and you can see that it's a really tight, snug fit. Well, I don't want a really tight, snug fit because I can't seal it. And a tight, snug fit between a hole that's cut in the panel and sliding a piece of copper pipe through it isn't tight enough for me. I want to be able to go back in and seal up around it. The rule of thumb I tell all my tradesmen, if whatever size you're going to put in, cut it an inch bigger in diameter. So I've got at least a ½ inch around the outside of whatever you put through my wall panel, so I have room to go back in and foam it up. I can foam it up with a single or a two-part component foam and know that I've got a good tight fit. So don't cut too tight. Make sure you leave room for that penetration to be foamed up and sealed properly. In this series of photos, I'm showing you two ways that a plumber put in a lot of pipe. The one on the left, there was some planning done for it, and you can see where it was framed out and they combined SIP and framing so that the plumbing was able to be recessed into the wall. It was something to be planned for. My guess in this slide you're going to see that eventually it would have been foamed up and sealed back up. The one on the right, they just cut into the panel and pushed those piping back into the panel. There was no planning for it. What's really odd about this is the picture on the right was done in a basement. It could have easily been framed out in a wet wall, or a chase could have been put around it, and the plumber actually would have had an easier time doing it had they done that. Now in this scenario, I'm not sure what they were thinking. This location is right behind a kitchen counter. Had they given it any thought at all, they could have pulled the kitchen counters out. It was all custom work. They could have easily put all this plumbing to the inside of the SIP envelope and either in the cabinet or behind the cabinet, and yet they went through this elaborate scenario of cutting through the panel, essentially destroying again the structural integrity of the panel, taking out a lot of the foam, and then snaking all of this plumbing through the panel that actually was a whole lot more work. There just wasn't a whole lot of forethought in this one. Now I mentioned Studer vents, and again, Studer vents do something that does better than anything in SIPs. They're commonly used in kitchen islands, but when we start talking about working in SIPs and we want the fewest penetrations possible, or any energy efficient house where we're looking for tight envelopes, get those vents down to the bare minimum. The Studer vents will allow you to do that. If you've never used an air admission valve, I strongly suggest you look into it. As we let all of these tradesmen, the electricians and the plumbers, go through their work, know that you're going to have to come back in and seal them up. Wherever that wire goes through the wall, it gets sealed. Wherever that HVAC contractor puts a vent or anything through, you've got to go back up and seal it. These are some pictures that I'm showing you of things that weren't planned. They weren't thought out. And these aren't the things that you want to see on your job sites. You have to be thinking ahead. Now let's talk about HVAC, one of my favorite subjects when it comes to working with SIPs. It's rooted in building science, because it's really building science that tells us how we should design, how we should work with HVAC contractors so that the system of heating, ventilation, and air conditioning properly are designed and fit to the performance characteristics and the system of a structural insulated panel house. And it's important that the first thing you ask ourselves is, what is it we're controlling? With the HVAC contractor, you're controlling heat, you're controlling air conditioning, and don't forget the V, you're also controlling ventilation. All of these things have to be looked at almost independently and then defined how they're going to be calculated so that they work in harmony with this SIP envelope. And of course, you got to know what climate zone you're in. What climate zone is the question that you almost have to answer before, at the end of each question. What do I do? Well, it depends. What climate zone are you in? HVAC is no different. Matter of fact, it may be the most important because you have to know what climate zone is required in order to properly size things. And when I say size things, we're talking about properly sizing your system. How do we do that? It's commonly referred to as a manual J calculation. Manual J calculation takes into consideration the R values of all of your insulation from your slab all the way up to your roof assembly. It looks at the U values of your windows. It looks at the type of foundation that you have, and it looks at the orientation of your shading and your light exposure, and it determines what that total BTU usage or its needs are in order to be properly heated and cooled. In order to do a manual J calculation on a SIP house, you have to know what numbers should be plugged in order to get the right out. If you put garbage in, you're going to get garbage out. And if you're dealing with an HVAC contractor who has never designed or never worked with a manual J when working with SIPs, they may be relying back on too many things like rules of thumb, and they won't go through the scenario of a proper manual J to get the real numbers. The correct air tightness numbers that you need to use are critical to get the proper size of that system. This HVAC analysis does the one thing that's more important than anything for us. It properly sizes equipment. Now, why do we want to properly size our equipment? Well, the biggest reason is short cycling. Well, what is short cycling? In simple terms, let's talk about the automobile. If you're driving a car in the city and you're starting and stopping all the time, think about what your gas mileage is going to be. How efficiently are we operating that vehicle? Not very. How efficiently do we operate the vehicle when we're driving at highway speeds? Much more so. We're getting better gas mileage. We're easier on the car. It's going to last a lot longer. The same correlation can be used with your HVAC system. If it's properly sized, it'll turn on and it'll run at steady state. Steady state is what we want to run it at, because at steady state you have better efficiencies, you're going to wear it out less, it's going to be a happier piece of equipment. And most important, if you oversize this piece of equipment, think of it this way. You have a big, large air conditioner that turns on and very quickly drops the temperature of your structure. Well, most air conditioners only operate off the sensory of temperature, not off of humidity. But you have to remember that an air conditioner works to solve both issues, temperature and humidity. If you have an oversized air conditioner and it doesn't run at steady state, the coil never gets cold enough so that condensation can form, which is the dew point, and brings all that humidity levels down when your air conditioning operates. So now you have a big air conditioner that turning on and off in short cycles, and it doesn't remove the humidity. It's not uncommon, and you as the SIP builder or installers need to understand how important it is if the HVAC contractor or the owner doesn't go through the manual J doesn't do a proper analysis to determine what the size of that system is, all of a sudden you're going to have a house that may have an elevated humidity level. And we know what an elevated humidity level does to us because we talked about it back in the building science chapter. As the humidity level goes up, it might conspire to find those areas that you may not have properly sealed or that have maybe allow that high humidity to come in contact with a cold surface, and you've got a dew point. That dew point is condensation, and that condensation is a callback for you when it's really not your fault. It's the HVAC contractor using rules of thumb and putting in systems the way he's always put them in because he was used to putting them in houses that weren't as energy efficient and tight as the one that you just built. Now, in addition to having properly sized our equipment so that we avoid things like short cycling, we also are going to get a more durable structure. How are we going to get a durable structure? Because we're having the right humidity level. The house is happier. Not only are the occupants happier because they're comfortable in the proper humidity, but so is the house. So that promotes not only a durable structure, but a healthier, happier environment inside of that structure. It's also going to be more affordable to operate, which only helps you promote the efficiency and the affordability of the SIP package that you're out there promoting as either a builder or an installer. So this HVAC analysis does a lot of great things for us. It also defines not only the size of the equipment, it defines it in terms of BTUs, the BTU consumption in both heating and cooling. And once you have that number, that's a spec. It's a specification in terms of what size the equipment should be that any HVAC contractor can use in the bidding phase. And that's incredibly important because now it allows you to bid a spec and not just bid a set of plans when you start sending out bids to different HVAC contractors. The other thing the HVAC analysis will do for us is it'll give us a room-by-room air distribution. It defines the airflow and the flow rate of air to different areas within the structure, again, for optimal comfort within this structure. The HVAC analysis has to understand the person that does the HVAC analysis has to understand the proper R values and the proper infiltration rates. Now, this is where it gets a little bit tricky because infiltration rates are not necessarily known before you build the house. The R values, on the other hand, are known. We know what the R value of that panel is. The infiltration rate is really a function of how good a job you did as the installer. How tight did you make that system? How well did you seal it up? I don't think it's unrealistic to suggest when we start talking about air tightness, if we want to talk about air changes per hour, that the analysis or the manual J calculation use the number of 1 air change per hour at 50 Pascal. And that number is very important because it's a number that you can achieve with a SIP system when you do everything properly. I think you can do even better than that. In some houses, we're seeing numbers all the way down in the 0.2 and 0.3 range at 50 Pascal, which is an incredibly tight house, which is very affordable and very comfortable to live in. Now, let's go back to talking about bidding the spec. This is one of the things that I saw years ago when homeowners or people that purchase SIP packages would say, well, I bought this knowing that I was spending more, but I thought I was going to save money on the HVAC system. The problem was when nobody bothered to educate the HVAC contractor, he resorted to rules of thumb and putting in the standard size system that he typically put in that size house. So he didn't have a spec to design to. This takes the guesswork out of what size system you need to put in. Not only is it good from your benefit, knowing that you've got a durable structure that's properly sized and we're going to get the humidity out of the house, but it also means that that homeowner isn't paying too much for his system. It's the right size. And now everybody, when they bid the spec, you've got an apples-to-apples comparison for all of these bids. It's apples to apples, it's right-sized, it's optimized for performance, which is incredibly important, and it also is basically third-party endorsed because you've got that manual J calculation, or in some cases that third-party person that does that analysis of HVAC. You can go one step further beyond analysis and you can do HVAC design or duct design. And when we do this, we start looking at things like, back when we were talking about building science, which was keep the ductwork in the conditioned space. Good duct design means a good system. It means it performs at an optimal level. Duct leakage, as we said, can run upwards of about 20%. Well, if you have 20% duct leakage in an unconditioned attic or in an unconditioned crawl space, you're just killing yourself. You're not providing the type of system that you want to provide, or not anything that lives up to what the SIP system is. So you have to understand where this equipment gets located, what the duct size is, how much air is flowing through it, where the registers and the supply ducts are, where everything is located so we get proper air movement. We also don't want to use that old traditional method of putting all of our registers or our ductwork out to the exterior envelope above windows and doors. It put in that curtain of comfort. They wanted to put that warm or that cool air in front of the old leaky windows and doors. Well, the windows and doors that we use in today's house aren't old, they're not leaky, they're high-tech. They use high-tech materials. They're well sealed when they're properly installed. You don't have that cold area when standing in front of a window or a door. So we don't necessarily need that register right above it. Let's move ourselves into the modern technology of building properly, and let's bring our duct sizes down, keep them centrally located in the core of the house, and let's distribute the air that we need in the proper location and not run more duct than we need to. It'll keep our system just that much more cost effective. Now, the last thing in the HVAC chain of letters is the V. I always tell people, if they hire an HVAC contractor who doesn't have a ventilation strategy when working with a very tight house, you haven't hired an HVAC contractor, you hired a hack. Because that's really what he is. He's not paying attention to ventilation. And ventilation is just that important. If we're going to build a house tight, we have to be able to ventilate it right. And that ventilation strategy needs to be purposeful. It needs to be designed. It needs to know and understand how we're going to bring fresh air into the envelope and how we're going to exhaust stale, polluted air. And when I say polluted air, I mean polluted air because we live in it, we exhale carbon dioxide, we have smells and odors from cooking and cleaning products, or we have humidity. Humidity is a pollutant. We don't want excess humidity, so therefore it's a pollutant and we want to get it out. All of these things come into play when we start talking about our ventilation strategy. Now, this slide is very interesting. It comes from ASHRAE, American Society of Heating and Refrigeration Air Conditioning Engineers. Now, these really smart people got together and they created this chart to define what they call the optimum zone of the level of humidity. Now, if we look at this closely, we can see some really interesting things happen when we stay within this optimum zone. The one that I like to point out is dust mites. The number of people that are allergic to dust mites is huge. It could be anywhere from 30 to 50% of the population is allergic to dust mites, which if they live in a house that has an improperly sized system or it leaks or it's got excess humidity levels, it means that they have dust mites that are making their own house or their house is making them sick. Dust mites don't drink water. They absorb moisture. And a dust mite ceases to exist below 53% humidity. That's a really interesting statistic if you think about it. It means that you can make a whole lot of people a whole lot happier in their house if you could just keep that humidity level down below that 53% threshold. I refer to this chart a lot when I talk to people about why we should have the right level of humidity in a house. It truly is the optimum zone that we want to operate in. How do we get rid of humidity? Well, first and foremost, we right-size our system. When it's properly sized, we're going to have the correct humidity because of the way the air conditioner operates. But we also may want to spot ventilate, and we want to spot ventilate through an exhaust strategy. What is this exhaust strategy? It takes the high levels of humidity in certain areas and exhausts them out of the house. Typically, high humidity level areas are going to be the bathroom, the kitchen, and don't forget the laundry room. Now, we could go down and put the average exhaust fan that costs $39.95 and put it in there, and it'll rattle and bang around and it'll last for a few years. It might do what you want it to do. But let's think of a different strategy. Let's use timers, or more importantly, let's go one step further and even use things like humidistats. A humidistat takes a spot ventilation fan like a bathroom fan. It identifies when the level of humidity rises, for instance, when somebody turns on the shower and takes a long hot shower, and now the exhaust fan can turn on, exhaust that pollutant, which is humidity, until the level of humidity drops down to a safe, or dare I say, optimum zone. With this ventilation strategy, we've looked at a lot of different things. We're looking at a balanced system. Why balance? Because back in the building science chapter, we talked about the difference of air pressure and what it will do. If we have differencing air pressure, air is going to move, and we want to know where it's going to move and how it's going to move. So we need to balance that system. Ventilation systems can basically be designed three ways: exhaust only, or supply only, or you can go to a higher end ventilation strategy, which may incorporate something like an energy recovery ventilator or a heat recovery ventilator. But be very careful. Know which strategy is right for your climate. In different climates, different pieces of equipment work better, more efficiently, and you can justify the cost. You need to look at not only the installed cost, the cost of the component, how much to install it, but also the operational costs, which include not only the watts of the fan and how much energy it draws and consumes to cost you to run it, but also the maintenance cost of cleaning it or repairing it or changing filters and things of that matter. So there's a lot of different costs that come into this ventilation strategy. But rest assured, you need a strategy for proper ventilation. There's no such thing as building it too tight. There's only building it too tight and not ventilating it right. Now I talk about strategy. Here's the one strategy that I use that, again, the folks at Building Science Corporation have promoted, and we use this very successfully in the Mid-Atlantic regions. Relatively mild climate, but what we do is we simply use a fan cycler switch. For about $112, we've got a fan cycler detector that knows how long the air handler has been on. We bring in small amounts of fresh air through a ducted line, and that ducted line has a balancing valve in it, and it also has a motor-operated damper. Well, it's pretty simple. For $200 or $300, we have the installed cost of a supply strategy of fresh air that comes into the air handling system, which is already running. And with the right type of air handling system, our operational costs are very minimal. So these are a type of strategies where we haven't gone through the cost of an HRV or an ERV, but simply use what we already had and just put it to good use. There's a lot of different strategies for ventilation, and you need to look at all of them. Now, if we are in a cold climate, we do need to look at something like a heat recovery ventilator. Why? Because when we spend a lot of money to heat up air, we don't want to exhaust that air and lose all the cost of heating it. So what do we do with a heat recovery ventilator is we bypass those airflow streams so that we recover some of the heat and bring it into or transfer it over to the fresh incoming air. And that exhausts the stale air, brings in fresh air. We've got a balanced system. The energy recovery ventilator is one step beyond a heat recovery ventilator because in addition to recovering the heat, it also uses a desiccant wheel to transfer humidity. So if we're in environments where we want to discard high levels of humidity or hold on to levels of humidity, depending upon, again, our environment where we're living, the energy recovery ventilator may make sense as part of that strategy. I want to drop down a few levels and go into crawl spaces because it's a big part of the HVAC job or the tradesman who's doing the HVAC work. If we're putting in a crawl space, I hope we're doing it as a conditioned crawl space for so many reasons. This conditioned crawl space is the perfect environment for locating this HVAC equipment, not just the air handler, but also the ductwork, because we're inside that conditioned space. We're not worried about losing heat or cooled air that we've spent money to heat and cool through a leaking duct into an unconditioned space. The conditioned attic is the only way to do it. If we look at some of these scenarios, you can see how we're going to make sure that we've got a covered floor so that we don't have any ability for any moisture to move up through the floor or through the ground, because there's a lot of moisture in the ground. And we're also insulating those walls. In that crawl space, we want a nice high R value so that we've completely insulated that wall. It shows just different ways that we're going to think ahead as opposed to filling up our floor with a whole bunch of insulation and putting in vents just to let hot, humid air in the summer into our crawl space where we're going to have condensation problems. Now, once we've done all these things with the HVAC contractor, we want to be able to test the envelope. And then we typically are going to test the envelope after these contractors have finished their work. Why? Because, as I said before, those contractors, if they're not paying attention, they may mess up what you did in installing a perfectly good system and sealing it up nice and tight. So, how do we test? We're going to test this envelope with what's known as a blower door test. The blower door test is an integral part of getting a HERS score. We know what the HERS score is because that's the score that tells us how good we did at making our entire house work as a system. The blower door test gives us some very clear numbers. These numbers can be defined in either air changes per hour, or they can also be determined in cubic feet per minute. One is just a measure of flow, the other one is a measurement of flow as it relates to volume. Either are usable, both tell us how good a job we did at sealing the house. I encourage every one of you to use a blower door test to test every single structure you do. Why? Well, first, it'll help you find mistakes. It'll help you find leaks that you didn't know about or that you didn't catch. You can use the blower door test while it's running, while you have your house depressurized, such that you can feel the air leaking into these different areas. And we've got a couple of tricks while we're doing this blower door test. We can use smoke pencils, we can use fog machines, we can use different types of tools to expose just the smallest pinhole leak. Once we get this envelope tested and we know that it's performing very tightly, we know that the whole system is going to work together. It's going to be a system that, if it's really airtight, it's going to give us good performance at low cost. Now, the blower door test looks something like this. We take a jig and we put it in the front door of the house. We turn this fan on, and this fan is hooked to the computer, and we measure the amount of air that flows through that fan in order to maintain the difference of pressure between the inside of the house and the outside of the house at about 50 Pascal. 50 Pascal is about the amount of pressure that it takes to raise the water in a drinking straw about 1/4 of an inch. Doesn't seem to be a lot of pressure, but that's the amount of pressure that it is. It's enough to move a lot of air. Trust me, if you put that kind of pressure difference across your wall, the air on one side is going to want to find its way through to the other side. Now, under 50 Pascal, a leaky house is going to be somewhere in the neighborhood of 10 to 20 air changes per hour. A nice tight house is going to be down in the range of, say, 1 to 4 air changes per hour. If you look at something like the passive house standard, which is a standard of building houses commonly used over in Germany where it started, they're looking for standards of tightness down around 0.6 air changes per hour. It's an incredibly tight house. The goal that I would encourage you to shoot for is somewhere around 1 air change per hour at 50 Pascal. If you can hit that number, you are a long way towards having a properly sized house or a properly performing house. Now, the duct blast is very similar to the blower door. The duct blast is the same thing. We hook a fan up, we pull air through the ductwork or push air into the ductwork, and we determine how leaky it is. We don't want our ductwork to leak. If we have leaky ductwork, especially if it's in an unconditioned area, we might as well be throwing money out the door. I show this picture because it is all of those things that incorporate the trades that we've now talked about: electrician, plumber, HVAC contractor. They all have their hands in this, what you see right here in front of you. And that is not a very good plan to seal. They've put things in the way that don't allow you to get in and seal up floor joist cavities or things of that nature. It's a perfect example of how not planning is going to make it difficult for your project to perform to the level that you want it to perform. And the very last thing that we're going to talk about in this chapter is going to be combustion appliances. If we think about how tight we just made our envelope, there's one key element that we have to make sure we pay particular attention to, and that is combustion elements. If we have a fireplace, a wood stove, if we have a gas heating water heater, all of these things have the potential to backdraft and bring in dangerous fumes inside the living environment if they're not completely sealed. It's absolutely important that we have a sealed system that brings in combustion air so that the piece of equipment can operate properly and all of that harmful fumes can also be exhausted. We've got a tight envelope. We don't want bad things leaking its way into it. Okay, that pretty much wraps up everything we want to talk about working with the different trades. That's going to be in Chapter 8. We'll see you the next time.